Today, I want to derive the Hawking temperature of a black hole from its geometry, following Gibbons and Hawking. First, we need a few prerequisites. I'll suppose that you know what a Euclidean thermal path integral is, and that it is equal to the thermal trace over the spectrum of a theory. So we have some partitioned function z, which is a trace over the theory of exponential minus beta h, where beta is the inverse temperature. So beta is 1/t. And is equal to the path integral over the fields, weighted with some Euclidean action, where the path integral is compactified in time. So this is very important. The time, Euclidean time, is compactified with the radius beta. You can see this from the trace exponential minus beta h, where usually an evolution is exponential, let's say ith, then if t is an imaginary time I beta, then we get the Euclidean, we get the thermal trace. So we'll suppose that known. The second thing I'll suppose known is that the Schwarzschild black hole solution is a solution to Einstein's field equations of general relativity. And the metric has the form written there, where a constant is introduced, a radius, rs, which is called the Schwarzschild radius, which is equal to 2 times the Newton coupling g times the mass of the object that sits at the center of this spherically symmetric solution. The omega square is the round metric on a two-sphere, and r is the radial coordinate of the solution. So given all this, how do we derive the Hawking temperature? So we will suppose that this solution, when we go to the Euclidean, it contributes to the thermal path integral on the condition that it is regular. So you want a Euclidean time compactified solution to be regular. This will fix for us the temperature and will compute the temperature. So we might have a problem in the Euclidean solution. Let's write it. The Euclidean solution is just where we replace t by a minus I tau. So the Euclidean solution just flips the sign of the term proportional to dt square, because the metric components are independent of time. So the Euclidean solution is this one. But we might have a circle which is generated by the fact that we look at a finite temperature path integral. We might have this circle of time of tau, circle in time, degenerate at a particular point, and in particular at the Schwarzschild radius. So could there be a singularity there? This is what we're going to compute. So let's analyze this solution close to the horizon, where we might expect a singularity. And let's take a coordinate adapted to being close to the horizon. So we take a coordinate, or we set r to be equal to the horizon radius, or the Schwarzschild radius, plus some small fluctuation delta r. We'll compute the metric close to the horizon. And for that, it's useful to have the expression for rs over r, which is nothing but rs over rs plus delta r. which is 1 over 1 plus delta R over Rs, which is approximately equal to 1 minus delta R over Rs. So if we plug this into our metric and compute our metric to first order in delta R, we'll get that the first term is proportional to delta R over Rs times d tau square plus the inverse, so Rs over delta R times d of delta R, the whole thing squared, dr square, plus the Schwarzschild radius times the two-sphere metric. It is useful to introduce a new coordinate where we set delta R equal to rho square over Rs, such that d of delta R is 2 rho d rho over Rs. So then if we concentrate on the two first terms in the metric, because the last one is, or the last two are constant anyway, then our metric becomes rho square over Rs square d tau square plus 4 rho square over rho square, which cancels. Then we have d rho square. And then we have Rs square, both in the denominator and the numerator. So this is the final answer. Now we should compare this to the metric on R2. On R2, the regular metric has a behavior dr square plus r square d phi square, where phi is an angular variable identified with period 2 pi. If you have this metric, we have a regular metric at r equals 0. It's just the ordinary flat metric on R2. However, if the periodicity would be different, we would have a conical singularity at r equals 0. So if we compare this to the metric that we had, we take out a 4, then we see that we get 4 d rho square plus rho square over 4 Rs square d tau square. So then we see that tau over 2 Rs should have period 2 pi. Therefore, tau must have period 4 pi Schwarzschild radius for the Euclidean metric to cap off smoothly. At the former horizon. Which is at rho equals 0. So therefore, we decide that the period beta of tau must therefore be 4 pi Rs, which is equal to 8 pi g Newton times the mass. And therefore, the Hawking temperature of the black hole is the inverse of this. The Hawking temperature of the black hole is 1 over 8 pi g Newton times the mass. Now this very fast geometric derivation of the Hawking temperature does agree with the temperature that one calculates if one puts a quantum field on the black hole background and computes the ensuing radiation because of particle-antiparticle production near the black hole horizon.